Hello, this is the project for the reactor Bolshov Mощnosti Kanalny, RBMK, by Scott Elwell, Jim Pruden, and J.D. Sauer. The RBMK reactor was a common reactor utilized in Russia. In English, it is translated as the high-power channel reactor, also known as a light water graphite moderator system. The high-power channel reactor had many engineering shortcomings, but is best known for the failure at the Chernobyl power plant in 1986, which is the focus of our study. Hello, this is the project. Today we are going to cover an overview of the RBMK reactor, functional block diagrams, the reliability block diagrams, fault tree and event tree analysis for the core breach that occurred at Chernobyl in 1986, recommendations for how to improve the RBMK reactor, and a summary of our project. The RBMK reactor operates very similarly to other nuclear reactors. It has a nuclear reaction which is utilized to generate heat, which creates steam in the steam cycle that turns the turbine, which creates power that ends up leaving the reactor. The RBMK is different from most Western reactors in that the RBMK water is used only as a coolant for fission reaction and not as a fission moderator. In Western reactors, the water is a coolant and a moderator for the reaction, building in a natural safety feature because as the reaction builds and heat increases, the moderator transitions from water to steam, removing the moderator and preventing the slowing of neutrons required to sustain a nuclear reaction. For the RBMK reactor, the heat is added to the water, which then becomes steam in the separator. The RBMK utilizes a separate moderator, graphite as depicted, which has no such failsafe incorporated. As the reactor begins to increase temperature, the coolant incorporates more bubbles as it begins to steam under pressure, reducing the coolant properties of the water and allowing more neutrons to collect in the moderator. Both of these events begin to increase the temperature and output power in a vicious feedback loop. To make matters worse, introduction of the control rods, as what would happen in a scram, which is a procedure to lower all control rods to stop the fission process, leads to an initial spike in reaction and temperature, making the cycle worse before the reaction can be terminated. Depicted is the RBMK functional block diagram, comprised of two separate cycles, the nuclear reaction and the steam cycle, which combined output mechanical energy that is converted into electricity, which leaves the site. Here is the RBMK hierarchical functional breakdown of the system, starting from the output of the mechanical energy and bringing it down to the moderation of the nuclear reaction. The RBMK configuration flow graph shows the actual components utilized in the reactor to accomplish the functions as discussed above. Depicted is the RBMK hierarchical component breakdown of the system. Depicted is the RBMK hierarchical component breakdown of the system. Depicted is the RBMK reliability block diagram. The nuclear reactor is composed of two large functional areas, the nuclear reaction and the steam cycle. Both cycles must occur for the system to successfully function, and therefore both functions are in series and relying on each other to successfully perform the overall system goal. The steam generation function is a parallel function with two branches that contain a parallel and series connection. In order to turn the turbine which generates electricity, one of the branches of the steam cycle must be operable. Inside each individual branch, only one of the two pressure tubes must be operable to heat the water to a sufficient temperature required to generate steam in the steam generator, and are therefore in parallel with each other. The generators are in parallel with each other. There is a primary generator connected to the turbine, which generates electricity that flows both to the outside world and back into the plant to accomplish additional functions such as power and critical water pumps that keep the steam cycle flowing. There is also a backup diesel-powered generator that can work independently to keep the water cycling through the system in the event of the loss of the main generator to control the heat exchange from the nuclear reaction. Next, we're going to go into depth and look at the event tree and fault tree analysis that resulted in the Chernobyl mishap of 1986. As part of our project, we also went over a failure to scram and a power loss failure scenario, but due to timing limitations, we will only cover the core breach scenario in the presentation. Reactor core breach occurred when the primary generator was intentionally taken offline as part of a test, and there was not enough time for the secondary reactor to come online. This resulted in a failure of the coolant flow. The increase of steam and pressure also resulted in a fuel element rupture and a runaway power increase. Any one of these situations alone would cause a potential core breach. The failsafe against the breach are the control rods. The control rods were ineffective due to an initial reduced operating reactivity margin that was not accounted for. There were not enough control rods in place at the start of the mishap. That, combined with the intentional disconnect of the backup system and a lowering system failure of the control rods, prevented the scram of the reactor. The core breach reliability block diagram depicted describes what was shown on the previous slide with the two instances that had to happen for the core breach to occur. Therefore, they're depicted in parallel. The reliability was calculated and found to be, the top level event was found to have a probability of occurrence of 0.0004%. The core breach event tree analysis was created utilizing the probabilities determined from the fault tree analysis on the previous two slides. The initiating event was the loss of the primary generator, which in the case of Chernobyl in 1986 was actually created by the operators to test the system. The following events that would occur would lead to outcomes that are depicted on the right-hand side of the screen. Outcomes in red are core breach outcomes, which would result in death or serious injury of individuals near the plant. Outcomes in orange would just result in a loss of electricity, a loss of production from the plant. Outcomes in green, of which there's only one, would be the plant continues normal operation. My first recommendation would be to design the reactor similar to Western reactors by utilizing water as not only a coolant, but also as the moderator, vice the graphite. This would help prevent the out-of-control reaction increase seen in the Chernobyl mishap. The fault tree analysis shows that with the water as a moderator, power loss and a runaway reactor would no longer be potential failure points in the reactor, reducing the probability of a core breach leading to gate 1. Additionally, there would be a third AND branch leading to the top gate, where the water acting as a moderator would have to have an additional failure such as a leak or rupture to result in the core breach. The additional AND loop would significantly decrease the probability of the event because AND gates multiply in the probability matrix. My second recommendation would be for an automatic system to ensure an adequate operating reactivity margin is maintained. The ORM is manually controlled by the operators, who did not understand that in an effort to increase the output of the reactor following an unintentional cooldown, they raised the control rods and did not maintain a sufficient number of control rod surface area in the reactor to account for the conditions. As the right side of the fault tree analysis shows, if the sufficient number of control rods were maintained in the reactor, that AND gate would not have been passed, and the pressure buildup that resulted in a core breach would never have occurred. In summary, there were several glaring human factors as well as system design limitations which combined to result in the mishap of 1986. Safety-related design limitations included a secondary power supply which took too long to come online and power the coolant pumps in the event of a loss of primary generator power. Additionally, the system's graphite moderator system provided a moderator that provided a constant reaction control even as the reactor began to cascade with increasing power and heat generation. Improper operator understanding and no standard operating procedure to account for the graphite moderator system led to a dangerously reduced operating reactivity margin, which placed the reactor in a hazardous operating condition prior to a test that removed the critical primary power supply. Poor communication between shifts precluded critical pieces of information such as the number of withdrawn control rods and the status of the emergency control rod system, which was also taken offline for the test, from being passed from the day shift to the night shift who were operating the test. Following the mishap at Chernobyl, there were several procedural and design updates incorporated in the remainder of the RBMK reactors in the former Soviet Union. Most importantly, the safety features of the automatic scram system were made much more difficult to be circumvented. The flaw in the design that led to a spike in reactivity at the initial reintroduction of the control rods was also fixed. The remaining reactors at Chernobyl continued to operate into the year 2000, and there are additional RBMK reactors still operating today.